Dear member of community, we are meeting today around the topic of increasing the capacity of optical communication systems. But before that, I suggest you to follow this animation, which will help you to understand optical fiber cables and how they work. Then I leave the conference to Professor Abdelkerim Amari, who will talk to us about increasing the capacity of optical communication systems with the questions and answers of the conference community.
Okay, so hello everyone, and thank you very much for this opportunity. In this presentation, I will talk about increasing the capacity of optical communication systems, and we present some solution for increasing the capacity. Let's start first with this diagram here. It's known that optical fibers are widely used as communication systems, and it carries more than 99% of the transoceanic and it's also used for metro optical network, data center interconnect for different range with different detection, coherent detection for ZR next generation system, and direct detection for other data center interconnect. And it's also used for access optical network with passive optical network as backhaul for fiber to the home and fiber to enterprise technology, and also front haul for next generation and current generation 4G and 5G mobile network. To meet the ever increase of traffic demands, an increase of the capacity of optical communication systems is required to meet the increase of traffics driven by the emergence of new technologies like Internet of Things, sharing high quality videos over social network, and also recently due to the COVID-19 situation, home office and online meetings became more popular. So in this talk I will start by a solution to increase the capacity of the existing installed resources by using digital signal processing for Amperage mitigations, and mainly for nonlinear compensation, and also the introduction of machine learning for optical communication systems, and then information theory based solution for Constellation Shaping and FEC coding. And later I will briefly talk also about wideband optical system by considering other bands like in addition to C-band, like and also space division multiplexing via multi-mode and multi-core fiber technology. Let's start first with the DSP for Amperage mitigation. So it's known that DSP is a powerful tool to compensate for the fiber impairments and also components imperfections like CD and TNT for the fiber, and the imbalance and nonlinearity of the components, and the fundamental limitation of increasing the capacity of optical communication systems is the nonlinear effects in the fiber, and mainly care-induced nonlinear effect, because it's a power-dependent nonlinear effects. So by increasing to increase the capacity or the spectral efficiency, we need to increase the modulation formats order, going for high order modulation like nonlinear effects, known as the cell-phase modulation. Also, the use of a small gap band between WDM channel leads to the increase of the nonlinear interference due to cross-phase modulation, cross-polarization modulation, and also for wave mixing. backhaul system where signal amplification is required using EDFA, erbium doped fiber amplifier, or other types of amplifiers. The interaction of the ISA noise due to spontaneous emission with the signal leads to the stochastic nonlinear signal noise interaction. So there was a lot of work to research works to compensate for this kind of nonlinear effects, and using numerical solution, the main idea is to link and then inverse use the side for the compensation of the nonlinear effects, or also as pre-distortion at the transmitter side. The most or the benchmark and well-known techniques for nonlinear compensation is known as digital backpropagation. To get the best performance, and also it requires small step size and high number of steps per span to give to become more accurate and give good performance. There are other solutions using Volterra series and the perturbation technique to gives better performance than linear CD compensation, only considering chromatic dispersion and not considering nonlinear effects, but low performance than DPP. And thus numerical solution still complex for real-time implementation, and some research work to reduce the complexity by using machine learning. Then for the nonlinear interference, this backpropagation can be used also to be applied for more than one channel, for the case of WDM channel, so that it take into account the nonlinear interference and compensate for it. But in practical, it's not possible because you cannot have the information of the adjacent WDM channel. Hence, in the case of digital subcarrier multiplexing system with digital subcarrier multiplexing, which is also became a commercial technique, and it's used to improve the performance and to overcome the bandwidth limitation of ADC and DAC. And in this context of multiplexing, we can have the information on the adjacent subcarrier and then compensate for this nonlinear interference by applying the total field digital backpropagation. But also we can use a decision feedback equalizer structure. So firstly we detect the signal, then we regenerate the signal using a nonlinear model of the channel, and then we can remove the contribution of the adjacent subcarrier from the signal of interest, and this can work for both to compensate partially the nonlinear interference, but also the linear interference when considering super Nyquist or Nyquist WDM system, where there is an overlap between the subcarrier. And you can see here that this feedback equalizer solution provides better performance at optimal input power because it compensates for both linear and nonlinear effects and interference, while total field digital backpropagation gives better performance in the highly nonlinear regime with high input power, which results because it compensates fully the nonlinear interference. Let's move now to the second part with machine learning for optical communication systems. So machine learning for optical communication system is a hot topic now, and there's a lot of research work in this context. with different applications, mainly network applications, like performance monitoring, network optimization, failure detection, and also predictive maintenance. And there is some commercial solution in this context. But it's also used for Amperage mitigation of both the fiber and the transmitter and receiver components, and for other approach like modulation format identification. As I mentioned previously, so for this nonlinear decomposition techniques, because they're still complex for real-time implementation, machine learning has been used to reduce the complexity of techniques like digital backpropagation and perturbation-based nonlinear decomposition. Here we have an overview of machine learning techniques. So we have three types: unsupervised learning, blind approach, clustering and dimensional prediction. Then we have supervised learning that uses training samples for regression with one now neural networks approach with deep neural network and convolutional neural networks and so on. Then we have classification techniques, supervised as well, and we also have reinforcement learning. And so in this work, I use this classification technique to compensate for the nonlinear effect in the optical link. The main idea is to design nonlinear decision boundaries more adapted to the nonlinear fiber channel using training sequence. Sorry. So usually, and the standard way to do the detection at the receiver side is to use minimum Euclidean distance and do calculation of the distance between the receiver sample and the constellation points, and we get straight lines for the decision boundaries. By using this kind of classification techniques, we can design nonlinear decision boundaries, which will result in better performance, because as we can see here that at the edge we do not have a Gaussian-like circular noise, but we have a different shape, not circular. And by using this, by designing nonlinear decision boundaries, we can get performance outcome. Have some results for Parsons window machine learning techniques versus the minimum Euclidean distance for two types of system: dispersion managed, where the dispersion is compensated in line using dispersion compensated fiber (DCF), and dispersion unmanaged, where the CD or chromatic dispersion is compensated using DSP at the receiver side. So we consider 10 gigabaud sample rate and 1200 kilometer. And for dispersion unmanaged, we have performance improvement 0.2 dB at optimal input power in terms of Q factor, and 0.5 higher gain for the dispersion managed with DCF fiber. By increasing the bit, we can see that we almost have no gain for dispersion managed, unmanaged, and smaller gain also for dispersion managed. And this is, if we look here at the constellation at this point, we see that we have kind of circular Gaussian noise, and in this case, minimum Euclidean distance is actually the optimal way to detect the signal, and then we cannot get performance improvement in this case, which also follows or the literature, because it's known that for long haul system with dispersion unmanaged, that the accumulation of dispersion and this interaction with nonlinearity result on the Gaussian-like noise and is well modeled by the so-called Gaussian model or Egian model. So mainly this techniques works well for short reach, low with this, and also dispersion management, but for long haul with large bit rate, which is the next generation system, requires this kind of system parameter. We do not get performance improvement. This kind of techniques does not compensate only for the nonlinear effects, stochastic nonlinear effects, but also performance improvement. The linear regime, because of the imbalance, we can compensate for the imbalance, IQ imbalance, as it's shown in this constellation. We'll move now to the third part with information theory-based approach for performance improvement using FEC coding and constellation shaping. So FEC coding is well-known techniques to detect and correct errors in the digital data or noisy channel. It's a fundamental technique and is used mainly in all communication systems. And the main idea is to add redundancy or parity bits to the information bits, and those parity bits have some information on the data, and then use them at the receiver side for the signal detection and correction. For example, when considering graph-based codes like DVC codes, those parity bits are XOR operation of the information bits, and then at the receiver side for the first bit, for example 1, we use information, receiving information of this bit. Then also the information contains in the redundancy, and we do some cross-checking, and we can detect errors if we have errors and correct them. This leads to the improving of the data quality at the given SNR, and also reduce the required SNR at fixed bit error rate. So here we have bit error rate versus SNR for uncoded and FEC coded signal. And at the given bit error rate, post FEC decoding, which is mainly the standard value is 10 minus 15 in this case, bit error rate, 10 minus power 15. The reduction in terms of SNR is known as the coding gain. So the coding gain in dB is difference of SNR between uncoded and coded techniques. This coding gain vary, of course, for different codes, and also for the way of the decision at the receiver side. So we have two types of decision: soft decision, ST, and hard decision. The main difference that for the hard threshold, and if we are in this side, so it's 0, or the other side it's 1. For the soft decision, it uses some soft information, probability-based calculation, and known as log likelihood ratio. And then we have multiple soft decision thresholds. In this side here, it's 0 with large confidence because we are in the middle of the probability density function, while in this area it's still 0 because we are in this side with respect to the hard decision threshold, but with small confidence. So by using this soft information, we can get improvements from 2 dB gain over hard decision decoding, but by introducing higher complexity. So we always have the trade-off between complexity and performance. Different RTC codes have been standardized over the years for the Asian systems, with, for example, for next generation 400G base, Reed Solomon code is used with hard decision. So we have short reach. We do not allow a lot of complexity and latency, so it's good to use hard decision decoding with here in this case Reed Solomon. And for long haul next generation system, we use soft decision decoding with staircase codes, and was using also soft decision with RDBC and turbo codes previously. The aim of the forward error correction is to correct errors, Gaussian noise errors, and then approach the channel capacity of the channel. And another way to do this is to use Constellation Shaping. So Constellation Shaping aims to close the gap with the channel capacity by targeting the Gaussian distribution, which has been shown to be optimal for the IWG and linear channel. And if we look at this figure here, this is the black line is the IWG and capacity, and then we have different QAM modulation formats considering the two polarization for the fiber channel. We can see that for low order modulation like QPSK, we are close to the channel capacity, but by increasing the modulation order, we have a gap with the channel capacity, which increase and asymptotically achieve 1.53 dB. And Constellation Shaping aims to close the gap with the channel capacity and improve the performance up to 1.53 dB. There is two types of Constellation Shaping: geometric shaping, which uses non-uniform spacing between the symbols, and probabilistic shaping, which uses non-uniform probabilities with uniform spacing. So here we have the constellation of 64 QAM shaped signal. We can see here we have the PDF or the probability of occurrence, that the inner constellation points have more occurrence than the outer corner points. And this is to target the Gaussian distribution in continuous time or Maxwell-Boltzmann distribution in discrete time, which is the optimal for the IWGN channel. And this leads, of course, to performance improvement via engaging the ASANAR or UASANAR in the case of optical channel. Another important features for probabilistic shaping is the finite granularity and the rate adaptation, which is a key technology for future elastic optical networks. So for elastic optical networks, the spectral efficiency will be adapted according to the reach and bit rate. And this can be done. Then we need to have flexible optical transponders or emitter, and this can be done by using probabilistic shaping. So we can have even fractional spectral efficiency like 4.5 or bits per symbol, which is give more flexibility of the transponders so that we can achieve better performance in the case of elastic optical networks. So here I will not give a lot of details. The main idea is that for IWDM channel, we can achieve the highest shaping gain at infinite shaping block length, because there we can achieve the distribution, the Gaussian distribution. While in this work we show that for the fiber channel, the nonlinear fiber channel, short block length shaping provides better performance, because it has also nonlinear tolerance in addition to the shaping gain. And then we need to pick the right algorithm for the shaping, the realization, the shaping, or it was at short block length. Here is the block diagram of the probabilistic shaping or probabilistic complete shaping scheme. So we have we do shaping first, then we apply ATC. And at the receiver side, it's the inverse way. And this is very important because probabilistic shaping is a kind of frame-based approach. So if we have a block length of 1000 amplitudes or symbols, if we have one error, the entire 1000 symbols will be errorless. And then when doing ATC first, decoding before the shaping, then we can ATC can give us bit rate lower than 10 power minus 15, so that we can overcome this issue with frame based probabilistic shaping. Here we have some results. So as I mentioned, at short block length we get better performance in terms of nonlinear tolerance, while for long block length we get the highest shaping gain, and then we can achieve a trade-off and optimal shaping block length between that give us both shaping gain and nonlinear tolerance. And you can see that by applying probabilistic shaping using different algorithms, we always get much higher performance than uniform signaling at the same bit rate. For dense WDM system where the nonlinear tolerance, nonlinear interference is high, you see that we found that also shaping give much better performance than even nonlinear decompensation via complex digital propagation. Complex in terms of complexity, high complexity digital propagation. And by doing some multi-dimensional shaping, we can get better performance. Let's move to the fourth part with wideband optical system. So previously, for optical communication system, C-band was used for transmission. So we fill this bandwidth or wavelength range with WDM channels in the C-band, and we use erbium doped amplifier for long haul system to amplify the signal. And recently, to increase the capacity, L-band was also considered. So we have C plus L-band. It's already a commercially available technology with a new 800G for different companies, Pinera for example, and still use erbium doped amplifier because EDFA can give us good performance in this band with C plus L band. One of the challenges is the increase of the stimulated Raman scattering, which leads to the transfer of power from high frequency to low frequency. And by considering larger bandwidth, larger bands, S plus C plus L, which is currently on the research topic, we get more and more challenges. So this simulated Raman scattering will increase significantly because you have larger spectrum now. And then there were other issues related to the components, because the components that we have, the IQ modulator, the coherent receiver, and so on, are designed for C-band. And by going to L-band, there was no big deal. But for S-band, there was has been found that there's some IQ modulator have wavelength dependency and then are not suitable for the case of S-band, and leads to the increase of the imbalance. So some imbalance compensation needs to be done at the receiver side. There is two ways now investigated to use the S-band, transmit in the S-band. The first way is to use C-band components because there is no other choice, and then compensate the imbalance using KPSP. And the second approach is we can use the C-band components and generate the signal in the C-band, but then doing wavelength conversion to the S-band and transmit in the S-band. Another issue with the S-band transmission is the amplification, because the ADFA does not give the bandwidth, does not cover S-band and does not give required performance. So some of the solution is to use helium doped amplifier, EDFA, for S-band and EDFA for both C plus L-band, or using other kind of amplifier like semiconductor amplifier or Raman amplifier. The main advantage of Raman amplifier is that it does not require. For example, here we have a doped fiber with atrium, but for Raman we can use the fiber of transmission itself, like single mode fiber, to amplify the signal. So we use the molecules in the fiber itself. But there are also some challenges with Raman amplification for bump optimization, and it also has higher cost than EDFA, and also the last approach presented here, multiplexing, is the capacity according to the number of cores or mode in multi-mode or multi-core fiber, or also fibers when we start multi-fibers together. And this increases significantly the capacity according to the number of cores. For example, here we have 7 cores. We can increase the capacity by 7 in this case. When talking about multi-mode fibers, it's not new technology, it's the old technology with tens of years, and we use it in some standards for SR data center, and reach of 100 meters between the data center. But when we go for long haul, we have some issues with we need to design amplifiers that work for multi-mode case, and for multi-core and again also for multi-mode fibers, we need to replace all the existing single-mode fibers with this new kind of fiber, which is not a cost-effective approach. So multi-core and multi-mode fibers can be used in new lines, but for existing single-mode lines and connection with single-mode fiber, it's better first to exploit more efficiently the available resources via wideband or DSP and shaping and so on. Then, in long term, we can replace that fiber by the new types of fibers. And so, also another issue, complex and will have multi-core with WDM system and so on. To conclude this talk, so non-native compensation, mainly for care and use of nonlinear effects, enables increase of capacity because we can transmit at high power. Then we can use higher order modulation, which has, of course, high spectral efficiency, but suffers from high implementation complexity for real-time systems. And then machine learning can be used in this case to reduce the complexity, but it's a powerful tool and it's not only used for this reason, but can be used for network optimization and other applications. For constellation shaping and HEC, can close the gap with the channel capacity and then provide high performance. FECs are a standard and fundamental technique for all kinds of communication systems. And constellation shaping or probability shaping is recently also became a commercial product with the Infinera 800G ICA6. And wideband system and space multiplexing enables higher capacity than the other approach, but and are considered as promising approach for future high capacity system. That's all from my side, and thank you very much for your attention, and I'm happy to answer your questions.
Merci, Monsieur Amari, pour la présentation intéressante. Par la même occasion, vous remercier. Vous avez honoré notre conférence. Sans trop tarder, pour l'ensemble des participants, si vous avez des questions ou des remarques, il suffit juste de cliquer sur l'icône main en bas. Monsieur Bouaga, vous pouvez poser la question.
Bonjour à tous, bonjour tout d'abord. Et je remercie M. Amari pour sa présentation très claire. Et donc, sans tarder, j'ai des questions si vous voulez. Oui, merci M. Amari. Donc, la première question, monsieur, c'est dans le domaine des télécommunications optiques, quelles sont les conditions, surtout si on part sur la partie de réseau, les réseaux LAN, c'est-à-dire la couche d'accès. Quelles sont les conditions pour avoir une transmission optique fiable, si on veut dire comme ça? Quelles sont les conditions pour avoir une transmission ou la communication fiable dans le domaine de télécommunications optiques, bien sûr. Donc, la deuxième question, pour les techniques d'accès, si on part sur des diamants ou sous-diamants ou même WDM, quelle est la capacité pratiquement sur capacité de multiplexage sur un bras dans le domaine pratique? si vous voulez aussi. J'ai deux questions. Après, j'ai deux questions. Ça va.
Okay. So, for access system, I guess you are talking about passive optical network in this case. Yeah.
Voilà.
Okay, so I do not have honestly exact answer for your question, but what I can say for like next
Voilà.
generation system and we do have for passive optical networks as 5G or FTTX fronthaul. Which generation will use we consider TG 50 gigabits per second as bitrate, and it uses EML for modulation, externally modulated laser with TDMA, I think, for TDM for uplink, for downlink, and TDMA for uplink. And you use also LTVC codes for FEC, forward error correction codes. Then, in this context, there is also another emerging technology called point-to-multipoint solution with XR optics, introduced by Finera, and got a lot of attention in this last conferences, which consider point-to-multipoint and this make the system less complex and more efficient. I'm not sure if this helps on your question. Is this okay for you? I mean, do you have other questions in this context?
Et comment fait la technique, le type de modélation à utiliser? QAM.
Still use, yeah,
Est-ce qu'on peut,
still use the direct detection. So it's used like PAM4 in this case.
ok. Thanks, monsieur. Et comment, pour le type de modélation QAM,
Yes.
quels sont les avantages d'utiliser cette technique pour les systèmes de télécommunication optique? Parce que nous avons vraiment un problème dans les types de modélation numérique. Donc, quels sont les avantages de ce type de modélation?
Okay, for QAM modulation. Yeah.
Voilà.
Okay, so there's two things here. First, QAM modulation is used with coherent detection. So when we talk about long haul system, high reach, high transmission distance, it's always now use coherent detection because we can we have more degree of freedom. We can use polarization, two polarization to double the capacity, and then we can use QAM modulation, I and Q, with high order modulation so that we can increase the spectral efficiency. And this goes also even for short reach system like 400 GZR in next generation 400 GZR will consider using coherent detection as well. So for coherent detection, by using QAM modulation, we can increase further the spectral efficiency because it has high spectral efficiency. For short reach, still direct detection is used because it's low complex, and then you can use band modulation to increase the spectral efficiency. So, yeah.
Merci, voilà, pour vos réponses. Merci, très clair. Je rends la parole à Madame Slimane.
Merci, Monsieur Ouaga. Donc, je passe à Monsieur Belchérif. Vous pouvez poser votre question.
Donc, Abdelkerim Amari pour cette intervention dans notre journée. Juste, j'ai une petite question. Dans le diapo 21, vous avez deux mesures où j'ai constaté l'utilisation des filtres et des amplificateurs en les types des types d'amplificateurs. Est-ce que c'est ordinaire ou bien spécifique? La deuxième question, wideband optical ou bien la bande passante optique. Quelle est la différence entre cette bande optique et une bande passante ordinaire? Quelques passe-bande, passe-bande, multivôte, etc. Merci.
Okay, merci. I will speak in English. So, for the first question, okay, so here is a simple experimental setup, and we use here optical amplifier, EDFA, bloom double fiber amplifier, and the filters here, optical filters as well. And I think I don't remember well, but I guess it's baseband filter. And both of them are optical, so it's the amplifier and the filter as well. For the second question, here we talk about the optical wavelength, optical bands, in which we can do optical transmission, and it was what was used for several years is just the C band, in which we have the wavelength between 1530 and 1565. And when we have a WDM system, so the WDM channel will be in this range, in this spectrum. When we talk about the frequency, but then this is for long haul system and long haul system. When considering like short reach system, we want to transmit at low dispersion because we will not use DSP for compensate of dispersion, and there is a lot of system using O band in this case. If we look at the dispersion here, in the O band, we almost have this region here, zero dispersion. So they transmit in the O band for short reach because we do not compensate for CD. It requires it's complex, and in short reach system, we don't like to do complex stuff. But when we talk about long haul and oceanic transmission, it was using C-band, but then recently with this emergence of high bandwidth applications, an increase of the capacities strongly required. And then L-band, this region is currently used. The research topics focus on also the S-band in this case. Is this your question?
Oui, évidemment. Merci de tout à l'heure, Abdelkerim. Donc,
Merci, Monsieur Ben Sherif. Monsieur Ben Mousset, vous pouvez poser votre question.
Thank you, Madam Suleiman. Mr. Amari. So, thank you for your presentation. I introduce myself. I am a teacher in telecommunication at University of Emotion. Mr. Amari, I have two questions if it's possible. Knowing that I am not in the field of optical. So, Mr. Amari, you spoke about artificial intelligence, optical transmission, and error rate. As you know, a good transmission is a transmission without error or almost its figure. So my question is about can we predict the error rate in optical transmission and to have at the end a good error rate? It's my first question. And still with the use of intelligence artificial, do you think that the optical domain really needs mechanisms like machine learning? If you can give us a small example, if it's possible. Thank you.
Okay, thank you. So for the first question, yes, we can. We cannot predict bit rate like in wireless communication. You can have the equations to get the bit rate. Here we have to do some simulation, and we have to consider this effects in the fiber and components, and do properly compensate for these effects like chromatic dispersion and so on. And then we can estimate with a rate using Monte Carlo estimation or Gaussian fitting or so on.
Okay.
Then we have to, of course, get very low bit error rate. But when considering FEC, we can, for the simulation, we can consider pre-FEC bit error rate, and then with the FEC threshold, can get error-free or very low error, 10 minus power minus 15 and so on. So usually what we do is to consider FEC bit error rate pre-FEC, or we consider also SNR and other performance metrics as well, like Q factor or material information or so on. For the second question, yes, machine learning is can be a powerful tool for optical communication as well, especially in the network side, network optimization and performance monitoring and so on. And I see that there is some commercial products using now this machine learning techniques in this context. For the fiber and components and performance mitigation, there is a lot of research work. I'm not aware of some commercial products in this context, but there is a lot of research work for different kind of impairment mitigation, and especially for complexity reduction of nonlinear decompensation techniques, because we cannot use them in real system because they're very complex. And by using neural networks to do some estimation instead of mathematical calculation, we can reduce the complexity. Do you have other questions?
Merci, Monsieur Ben Mousset. Monsieur Dubin, vous pouvez poser votre question maintenant.
question, it was very intensive. Really interesting for of students, research, PhD students. My question is about quite fine. Could you please? Okay. Right here. You have here the PR with launch power. My question is about the launch power. We have same value of different launch power. For example, -6 and +6. We can have same PR, different launch power. So how we could get this value, or there is need for this.
Okay, I'm not sure if I understand your question, but I guess that you are talking about why we do have this shape of the layers, right? Yeah, so the point is that the nonlinear fiber channel, the signal is, as the case of wireless communication, is limited by noise at low input power, but when we go to high input power, it's limited by the nonlinear effects. So we have to find the optimal input power that we can use for the transmission that have a balance between noise and nonlinear effects. We see in fiber in optical communication a lot of papers showing this kind of figures, varying the launch power into finding the optimal one that is the best figure. Does this answer your question?
Can't hear you very well, Mr. Abdelkerim.
Do you hear me now?
Merci, Monsieur Depin.
I think it was the problem with sound. I don't know if
Okay, I can repeat if you hear me now.
No, I can hear you now. Yes, I can hear you now.
Okay. Okay. So for optical communication system, because the fiber, the optical fiber is a nonlinear medium, the signal is limited at in the low input power by the noise, as the case of wireless channel as well. But in the high input power, there is a limitation also because of the nonlinear effect, which is power dependent. The higher is the input power, the higher is the nonlinear. So we always need to vary the input power or launch power so that we can find the optimal power in which we can use it for transmission that allows the VPIphotonics. Is it clear?
Okay, we thank you for your assistance. You next time in the next edition for this conference.
Okay.
Merci, Monsieur Depin. Monsieur Duncan, vous pouvez poser votre question.
Dr. Amari, for your presentation. I have one question. I can use your technique or your method for two optical fiber and photon. Sorry, could you repeat? I didn't hear well the question. I repeat my question, please, Doctor. I don't hear you. I'm not sure if it's a problem, but yeah. Yes. Okay. I can repeat my question. Yes. My question is, you can use your technique or your method for two typical so that's plastic and cotton. Is this a type of fiber or? Yes. The two type of fiber. Okay, so I'm not sure what kind of fiber it is. It's like, if it's like standard, I don't know, single mode fiber or this kind of fiber, yes. If it's highly fiber, maybe can work as well, but I'm not sure about this fiber. If you can maybe contact me later by email and give me more details, and I can answer your email later. Thank you. Welcome.
Je vous remercie.